present.
Well, yes, I am seeing it now. Yes, indeed.
Cool. All right, here we go. So this is the recap for the season finale, season 14, episode 20. Now, before we begin here, I want to give a shout out to this gentleman here, the Vault of Truth 923. He put together a 8-hour something 150 flat earth proofs. It's a really nice listen to. Like if you enjoy audiobooks or long form content, or you want to put something on while you're at work, if you have something like that, this is a great listen. Really fantastic video. So I'll put a link in the chat. Shout out to him. Definitely check out his video. It was an awesome listen. And subscribe to his channel. The link is right there in the chat. So Vault of Truth 923. Shout out to you.
Hello and welcome to the Vault of Truth YouTube.
Oops, didn't mean to start playing it. Meant to skip slides. Okay. All right, here we go. So as I was putting together the summaries for this episode, or for the season, I realized there was an overarching theme that was going on, and it was the concept of the celestial and terrestrial spheres and navigation by the stars, really the core backbone of what the globe model is and what ties it together. We've done presentations on optics in previous seasons, etc. But in this season in particular, there was a really, a really overarching theme about the celestial model that is presented to us. And yes, it was a pleasure to recap all that and put it together. So we're going to outline all of that now, because all of modern cosmology, our way of interpreting everything, is all based on this cosmological model that's been given to us, and the usefulness of this coordinate system called the graticule, which is latitude and longitude, and which represents the positions of where stars once were at a specific time. And based on this whole cosmology, or based on the position of the stars that we see, they've constructed an entire worldview, and where they say that they know where these stars are in exact 3D space, and they've constructed units of measurement to describe like a coordinate system within that, where they can describe light, thousands of light years, and and what that looks like in terms of a scale for them. So anyway, I just wanted to start by recapping with Copernicus. He warns us here that when the astronomers will use any useful tool necessary to make the point, and if their tools and models are working correctly, then uh, then that's all that they need. They'll do anything to make their equations fit, and once they fit, they don't care why it fits. They just care that it fits. And if you enter astronomy thinking that you're going to learn the physical meaning behind reality, or anything meaningful about why the celestial bodies move and stuff like that, then you're gonna leave a bigger fool than when you entered. So that was what he said regarding his conceptual model of the Earth being in motion and partaking in the celestial motion that is observed. All right, so here we go. Shane opened up on season 14 with episode 1 with the geodetic datum, and that is how they relate the measurements to the coordinate system, because without being tied to a coordinate system, none of the measurements mean anything. So they have this inherent spherical coordinate system that they're using, and all measurements end up getting tied to that. And the backbone of that started with the conceptual model, the conceptual two-sphere model from Ptolemy. And to use his model, you have to, assume that the Earth is a globe, because the way that it works, it's going to relate positions of the stars to ground positions for an observer at the center of the conceptual sphere. So what they do is, you can think about it like, suppose the Earth's a sphere, you're standing on top of it. They would want you to be in the center of it, looking up at the stars, and the stars would be at the surface of Earth. So you're at the center of a ball of 3959, and the stars would move at 60 nautical miles per degree and 15 degrees per hour, relative to that fictitious observer at the center. So following out that motion with the true positions of the stars, they create ground positions relative to that fixed position within their coordinate system. So they constructed a really neat time to relate angles and time together to this fictitious observer based on a 15 degrees per hour of a position of a star that you don't actually see, and the apparent position that you do see is astronomically refracted from that true position. So that's how they maintain the relevance of a ground position to the conceptual model of the terrestrial sphere as well. So that's how they link them together. And this is what it all started from. And this is the earliest known records that, or this is like the earliest book that survived the book Holocaust. And it references Hipparchus, Eratosthenes, and it's like one of the only references that has all that has that. But anyway, the way that it comes together, it's all built on this premise of this two-sphere model conceptually. All right, and then there's another conceptual model that's used. So the beginning model of this for the terrestrial sphere would be the ellipsoid model, and then there's the gravitational potential model, which is the geoidal model, and that's the WGS 84. and that's where they make astronomical terrestrial measurement corrections to astronomical phenomenon. So this is where they came up with the deflection of the vertical. So when they take a zenith measurement of a star and it's not exactly transiting at the time when they say it should be over at their zenith, they say that, well, their instrument actually isn't truly level. It's not perpendicular to the gravitational potential. There's some anomaly, and they have to uh, literally account for an angle offset to the center of the earth, and they take that deviation as a correction for the deflection of the vertical. And after applying that, they say, then you would technically be aligned with the zenith of that star. And they're like, oh, look, we lined up with our ground position hypothesis about the earth being a globe. So this is where all that comes from and why it's necessary to do that. And that's referenced in geodetic surveying, not your local state surveying, your plane surveying. Okay. And then here's a look at that geoidal model and the ellipsoid model and how they interact. So whenever there intersection differences, that's when the geoid's undulating, and that's where you need to, possibly correct your device to remain perpendicular to that gravitational potential. And you would never even necessarily be standing on this. This is a mathematical concept that exists beneath your feet conceptually. And how they wrap this, using this coordinate system is how they turn sea level into a curve level. So it's only curve level, within this coordinate system because it's defined that way with these fictitious coordinates here for the ellipsoidal model and the geoidal model intersections relative to mean sea level. Now, another important thing that was brought up on this is that they don't really measure the Earth in terms of curvature. They make measurements horizontally, and then they consult the positions of the stars, which is what we were looking at earlier with the deflection of the vertical thing. So it's all based off of astronomical corrections to define the terrestrial model, not the other way around. The terrestrial model doesn't define the celestial model. The celestial model defines the terrestrial model. Now, the celestial sphere is a sphere of infinite radius. The terrestrial sphere is a sphere of 59 for its radius. Now, because of the radius being injected into the terrestrial sphere model, you might be thinking, oh, well, that's what makes, the Earth a sphere or whatever. All that represents is the linear portion of when the stars are angularly descending from a zenith position down to the horizon. There's about like a 30-degree window where it actually follows 15 degrees per hour for the apparent position. And then it starts to deviate from that. And that's where they start to introduce different amounts of astronomical refraction per like unit of per 10 degrees of angular elevation. So if you're looking at a star at 30 degrees, the amount of astronomical refraction with respect to its 15 degree per hour position is going to be a specific amount. And then when you're looking at it at 20 degrees, no matter what the actual conditions are, that's also going to be another specific amount, so on and so forth, until you get down to the horizon, to the point where they have formulaic outputs that are derived from curve fitting models using expansion series, etc., to give exactly what it has to be to maintain usefulness within the coordinate system. For example, if you take a star in stellarium and turn refraction off, take its angular position to 0 so that it's like at the horizon, then turn refraction back on, you'll see it's refracted by like 15 or 20 arc minutes or something like that. Then you can drop the star down below the horizon in negative coordinates, and the star will increase in refraction because it just has to scale out the rest of its equation before it actually becomes occluded by the ground, and then the apparent position will get negative coordinates. Now, you'll never see the star get that low, absolutely. That's just to play it out in their thing to show how the refraction thing has to scale proportionally to maintain usefulness to the angular position that's moving at 15 degrees per hour no matter what, because the sky's a clock. Now it's moving a little less than 15 degrees per hour as it's sidereal, but they round it all to that. So within their coordinate system, that's what it can be considered. So
I find that kind of conspicuous, though. I mean, once a celestial body falls below the apparent horizon, how does one verify the measurement?
dude, so true. That's why, well, until the celestial theodolite and what you did with the sun shadow measurements, without that kind of terrestrial intersection, their conceptual model based off of apparent positions, like Copernicus said, could be physically meaningless, and you have, good luck. And that's exactly what it is. Because what the celestial theodolite shows is that the stars don't angularly descend at 15 degrees per hour for the observer. And what you showed with the shadow set measurements, the sun doesn't angularly set at 15 degrees per hour. Like the shadow sets when the sun is like 70% of it is angularly visible. it's absurd, what they've proposed. But because of the usefulness of this relationship to a position of a star to that fictitious observer's position, they have this whole coordinate system here, and the angular rate at which it descends is defined by the 60 nautical mile per degree, 15 degree per hour relationship. So that's all that defines that. But to merge those two together is what makes them both useful. But the positions of the stars is what defines the usefulness of the terrestrial sphere, not the other way around. All right, and then this is more on just latitude and longitude being the graticule, which just means the positions of the stars on the first cusp of Aries, which is the positions of the stars on the vernal equinox, and then adding 15 degrees per hour to those positions, no matter what. And then any angular deviation that you see apparently is astronomical refraction. And then all of that gets wrapped up in the ECF coordinate system and the ECI coordinate system, which are just coordinate systems that are defined with respect to the center of the Earth and then everything outward on the surface. And another major point here is that within the spherical coordinate system, there's something that Shane likes to call coordinate system simultaneity, which means that all coordinate systems are equally valid. Oops, I didn't get the thing for that. But basically, all 2D Cartesian, conical, spherical, all of those, all these Euclidean projections, as long as they have a common z-axis alignment, are all valid simultaneously at once. It's just a matter of a math function to relate the angle transfer to the other coordinate system. Sorry, I don't have the equations put up for it. I thought I'd grab those. But yeah, once you have this spherical coordinate system here for the positions of the stars, you mirror the same thing with an angular relationship to a star in the south, which we know from Chinese history from a later presentation that we're going to go over, that they did that with Canopus, the Chinese did, and they mapped out the same angular relationship to 60 nautical miles per degree for Polaris. And then once they had that, they were good to go. All right. So the symmetry of the coordinate system isn't based on, isn't necessarily based on the shape of the Earth. It's based off of what a single observer saw at one hemisphere at a specific time, and then what was later seen by another observer at the same time, doing the same thing. So like they merge these two based off of single observer observations at a specific time. All right. And then then Stone did a follow-up to to season 14, episode 1, episode 2 here, where we went into shadow sets. So geometrically, the Earth being a globe, the shadows are supposed to behave a certain way in response to the geometry of the relationship of the light source and the object casting a shadow. So if the sun is geometrically setting under the horizon, under the ball, then the shadows will be cast upward. And what will happen is, as the sun is setting, an object casting a shadow will cast the shadow higher than the object casting it. So for example, here you see this pillar is casting a shadow, and as it crawls along the ground here, it's going to actually crawl up this window and be higher than the pillar itself. The window casting the shadow on the wall is going to end up being higher than the window itself. And then in addition to that, there's going to be a constant sharp sweep of a shadow, and that's going to be caused by Earth curve. That's just going to overtake everything at a constant rate. It's just going to sweep it out. And so there's going to be a hard point where you don't see any shadows. And on a flat Earth, oops, I don't have that one. But on a flat Earth, the distinct difference would be that the sun is moving away. So we're going to get a point where the shadow stops raising at a constant rate, and it goes to zero. It basically just goes to zero, and it just stops, and then it fades. So on a flat Earth, that's the way it would work if the Earth isn't geometrically setting underneath you, and it's just moving away horizontally, and it's taking its light with you. Or, I'm sorry, with it. So Stone did this observation a couple of months ago, and this was a follow-up to a previous one that he did, where the Globe lads requested more data to verify the positions of everything in his house where he made the measurements. So he made some nice diagrams here where we have the exact measurements from where the window is located, where to the wall where the shadow is being cast, and then the exact height. He also has some outdoor geometry laid out for us. So at 228 meters away, there is a meter that's 16 meters high, higher than the actual window here that's casting the shadow. So he even accounts for the terrestrial terrain. But other than that,
actually, that's closer to 1,400 meters away, and the 228 is an elevational marking over top of the 212 where the house is. So there's 16 meters of rise over those 1,400. That's what we're about there.
Got you. Which will be accounted for later in the in the time that the sun sets in that shadow situation here. So you can't see it in the screenshot because I wanted to. Anyway, I just got these from YouTube, so the quality is a little low. But there's a position marker here for the height of the window that starts right here. So when the shadow starts, it's going to rise as the sun gets further away and gets lower in our angularly in our visual horizon. But on a globe, remember, the shadow is going to exceed the height of the window. So just keep this marker in mind here. So as the sun starts to set here, it rises to about here. And this is as high as it gets. And you can't see the thing here, but it is not higher than the window. It ends up being a little short. And how short exactly? Well, Stone has the exact measurements, but if I recall, it's 117 millimeters shorter.
That is correct.
Yeah. So here we got some nice graphs where Stone plotted out the angular descent rate goes isotopic, meaning instead of continuing with its linear curve at like a linear descent at 15 degrees per hour, it starts to curve flat where it's no longer appearing to drop. So this is what this indicates with the shadows here. And then again, he just inverted the data for this one so that you can see what it looks like on a descent, so that it's more, because you're conceptualizing it as the sun descending. So looking at it going up kind of, anyway. So this is what it looks like on the descent plot. You can see that it's not following the steady linear descent rate. And in here are little section increments where you can see the deviation from linear to where it starts to curve off asymptotically or asymptotically. Now, here's the exact measurement close up here, 117 millimeters in difference from what the globe predicts. So this is what you call a geometric failure for the globe. Now, if the Earth were a globe, they would predict that this shadow starts to exceed this window, and then another shadow sharply takes over from the ball curve, and just then you just can't see anything because it's dark out. Now that never happened, and then as you play out the video, the sun just or the shadow just fades out right here, instead of being a crisp, defined shadow that gets abruptly swept away. So what you can do with the angular difference in measurement for prediction there, and the height that the maximum height that it got to, and the distance from the window that cast the shadow, you can do a little trig there and get the angular elevation intersection for where the sun is at angularly. So in doing this, when you take the difference in these two angles, you get 0.34 degrees, which is 70% of the size of the angular of the angular size of the sun, which is 0.50 degrees in angular size. So the sun sets when the angular size is at 70 is like 70% visible. That's not what the globe predicts. That's what a flat Earth predicts for a sun that's moving away from you. So to kind of put that in perspective there, and anyone can repeat these measurements. So yeah, so this is a accounting for that hill elevation difference. This is what that looks like geometrically on the other end of this triangle here. So the sun being 70% visible, and then accounting for the hill blocking it as well. Now, the cool thing about that is it only requires your ability to measure the height over the distance of the object that's going to cast the shadow, and then you just need some wall for it to be cast on, where you're going to mark your measurement for the height of the object casting it. And then with that data, anyone can reproduce this. And I think, what was the amount of Globers you said that emailed you their data, Stone?
Oh, that'd be a big fat zero.
Oh no, none, huh? Dang.
No, we had Jeffrey on Twitter most recently who had difficulty with this experiment. First of all, failing to recognize that, like you pointed out, the shadow that I measured on the wall does not come up as far as the same height as its representative position opening on the door behind, through which the light is shining to produce it on the wall. That it never does come up the same height, that it comes up 117 millimeters short. This is the first point that Jeffrey had a really hard time even comprehending. Even last month, he was openly posting that the opposite occurred somehow in my data. That the shadow actually went above that height and kept on going, he said. And I'm like, no, pay attention. I actually quantify how far it falls short of the mark, not that it goes past the mark. And he waffled a little, and then he started to say, well, okay, well, how do I know that that mark on the wall is the same height as the one at the base of the window over there? I said, well, geez, come on, Jeff. I personally poured this slab before I put all the electrical, plumbing, structural built the forms for it all around, and, used a tube-based water level from one side of the form to the other side of the form to make sure the whole thing's level. How far out of level do you think my slab is going to be? Not quite 7 meters across the floor, one point to the other on the slab. How far do you think that's going to be off? And he finally he sat on the point that, well, I'm just taking your word for that, because you didn't show me any video documentation where you took a film of that and showed a level across, and you know what I mean? Like, it's been my open opportunity the whole time for anybody to go ahead and set that up and prove me wrong. But they would rather just sit and conjecture about what I'm still not showing them, and how that means it's not necessarily true. It's mind-boggling, the reactions that I've gotten from the Globies.
Yeah, that's super unfortunate. And they could do it themselves too. And like, in worst case scenario, you could like construct an apparatus to cast a shadow on something if you don't have a westward.
Even if you have a big window, is put a piece of cardboard up on it. You know what I mean? Create something on the other wall, anywhere. Like,
yeah,
so easy, so easy.
It's a really simple and straightforward one. So well done, Stone. And these diagrams are awesome. Really helps illustrate the importance there. So like, basically, if the Earth were a globe, these triangles here would be flip-flopped. Essentially, would be an easy way to conceptualize it.
We wouldn't have measured that 117 on the far right. That it would have just kept on going. It would have been eclipsed. It would have been occulted. You know what I mean? That out here where the 16 and the 24 are, where that peak is, that peak should have caused the shadow to go right up, blast past the whole window, and turn it all off. It should have sharply disappeared, and over a matter of about 2 minutes tops. There should have been a 2-minute climb across that window, given the angular rate movement of the sun at the horizon, et cetera, like you were describing already, that we didn't see any of that. There is no triangle. You can't measure a triangle like that until you have a position on the wall, which you're going to measure something that is measurable, fixed, like we saw in the data. But if the other model were true, that there is no fixed point there. It just goes by. It just goes from bright to dark immediately, sharply. And we never saw that. So no, there is no comparative triangle.
Oh, it wouldn't even stop, right? And then the other shadow would just abruptly end it.
Exactly.
Oh, for some reason I put it in my head that it would also eventually settle down on a globe, but just be higher. But no, as it's going up at that constant rate, there's going to be another one that's going to come out and just swoop it up. Yeah, so you wouldn't even.
The land itself.
Dude, that's hilarious.
16-meter peak would eclipse the window.
Gotcha. So the fact that the triangle exists at all is GG. Hilarious.
Yeah,
okay.
pretty much.
Gotcha.
The fact that it is still and fixed and you can measure it means that it's not the Globy scenario, because the Globy scenario doesn't involve something that stops. It just keeps going.
Yeah, totally overlooked that. Nice, dude. What an awesome presentation. Yeah, definitely go back and watch that. That's a banger. That was episode 2, guys. It kept getting better. Like it was awesome. So then the celestial theodolite update hit Globe Busters here. So we did a recap of that. And the celestial theodolite, of course, is using timing intervals in the coordinate system in which they have constructed with the position of the stars and seeing when there's a geometric alignment which causes an occlusion. And with respect to an observer at some distance relative to a mountain peak, we can do some trig to figure out what the relative angular size of the mountain should be if the Earth is flat, like what that intersection angle would be for a star to get occluded at. So by referencing those, we can make mutually exclusive predictions for what the globe would predict, because they're going to have a lower triangle. So with that, the star is going to get lower for the observer first in their coordinate system, because their coordinate system is observer based to make the celestial and terrestrial sphere merges. So they're going to predict an earlier occlusion timing, because the true position of the star relative to the observer is angularly descending at that fixed 15 degrees per hour. And if it's not, then the Earth isn't a globe, because the whole coordinate system is based on that, relating that point. So keep that in mind, that the usefulness of the coordinate system, let's say hypothetically that the star's true position doesn't actually move at that rate. But you would never know, because you only see the apparent position after you've taken your zenith measurement and added 15 degrees per hour to it. As you see it descend into the sky, it lingers beyond the 15 degree per hour point, but you have no idea, you would have no conception of that without having that initial snapshot. So based off of that, they have this entire coordinate system where the star moving at their angular descent rate of 15 degrees per hour should intersect with this mountain peak, which is also at a lower elevation because of the Earth curve that defines their coordinate system. And if the Earth is flat, then the star, which isn't truly angularly descending for the observer, will occlude at a later time when it intersects with the mountain peak relative to the mountain peak in their coordinate system. And that's what ends up happening. So to kind of look at the trig functions, we talked about what rise over run is, because we're using plain trig here for this, which is the basic form, the easiest form of trig that can be used. So we have the run here, which is 50,000 meters, the rise, which is the mountain altitude. If you do your arctangent of that, you get the angle output. That comes out to be 2 degrees and 31 arc minutes. And that's what you can do for all the mountain peaks there, and then for any relative mountain peak, and then you can subtract what the drop over distance would be for that amount, and also you can convert it into an angle amount as well, and then just subtract that from the flat Earth amount, and that's what the globe predicts. So there's multiple functions you can do to get the drop over distance. The easiest way is to do central angle and just divide the distance by the radius to get that angular amount, and then half of that amount is the drop over distance in terms of an angle, and then you just subtract that. So we went over the spreadsheet there, and here's an early looking back on this thing is hideous. Man, so we were just
I don't know, man. I think it's already prettier than most of mine. So
dude, I think it's in a pretty good shape now, but this looks rough comparatively. But anyway, we just went over all the different ways to calculate for what the globe would hypothetically want to account for. So this is just an early snapshot of what all that looked like. And if you want to go over the current version of the spreadsheet, a link can be found here, which I'll put in the thing here in a second. I'm going to tab out of this. Let me get the link. So if anyone wants the current link to the spreadsheet here, you can use this one. And also, there's the celestial bounty. So to give another update on why isn't this update? Do the thing where you work. There we go. Okay. The celestial bounty. So if you guys want to link to this as well, you can find out more information about that. We'll go over here in a second as soon as I switch back to the right frame. Okay. So the celestial bounty is the celestial theodolite measurement reward program. To give some context of what the celestial theodolite is, you have a recording device and you have a mountain peak. You point your recording device at said mountain peak and you watch stars descend into said mountain peak. When you're doing that, you need to make sure your recording device is synchronized to GPS time so that we can track back where the positions of the stars at that time relative to your position to figure out which stars are intersecting the peak. So that's very important to have that time synchronization component, knowing when you started your video, the current time. If you could put timestamps in your video, that would also be helpful. But just knowing the time in general is good. And then we also need to know your latitude and longitude coordinates for where you're recording from. And we need to know the name of the peak that you're shooting and the latitude and longitude components of it. If it's a well-known peak, it'll probably be on Wikipedia. So just having the peak alone, just the name will be fine. And then if you're not sure what the peak is, you can use an app called Peak Finder to identify the peak, download the local data relevant to your location, and then click Find Peak. And then you can use your phone app to look at the mountain and it'll tell you exactly what it is. Very helpful. Once you have it identified, you have all the necessary information to send to me to collect your reward. So there's a specific reward measurements in the north. I just changed the rewards a little bit because we just got some extra money to add to the prize pool. So currently there's a $500 prize pool and you can make up to $200 per measurement. And that applies to people that live in the Southern Hemisphere specifically. If you live in the Southern Hemisphere, any mountain peak measurement that is sub 80 miles is $100. Anyone that's over 80 miles is $100, or 100 is $200. And that's 128 kilometers for the kilometer lads. And then in the Northern Hemisphere, $50 per occlusion. And if you have if you're sub 85 miles, if you're over 85 miles, the reward price is $100. So the biggest deviations and measurements that we found for their coordinate system, like when the stars are lingering the most, is when the distance between the peak and the observer are the greatest. So the more distance, the more deviation there is in their coordinate system. You can take a quick look at that. So in North Peak, for example, they predict an angular descent rate of 15 degrees per hour, but they end up being off by 13 arc minutes for what Flat Earth predicts using their angular descent rate, and up to 21 arc minutes using their angular descent rate of 15 degrees per hour relative to just the observer. So this is like a huge catastrophic failure here. And then their refraction amount wasn't geometrically enough to compensate for the drop over distance either here, and because the star is actually its true position is geometrically below the horizon according to their 15 degree per hour 15 degree per hour angular descent rate relative to the observer. Just absolutely destroyed over this. So that's these are really useful to show the difference in their conceptual model and reality. So
there's one other thing I would add about what you can do to produce. Go back to the tab you just at and scroll up so we can see the graphic. There you go. There's the moon coming down and we're seeing things. We're looking to the west here, but the same thing can be done looking to the east as well.
Yes, absolutely. An emergence. So what you'll do is just face east, start your recording. Now for this, because you're not going to have foreknowledge of the star ascending unless you do some stellarium stuff, but it's not necessary. You could just go there, shoot the peak, and then just while you're recording, a star will eventually emerge from the peak. You just got to wait. You just got to play the old waiting game. But yeah, absolutely. An emergence is just as valid because it actually obeys the same physical process as having to overcome the intersection point, which is a big thing that we just realized in their coordinate system for the not to get too math heavy into it, but I just put out a video on my channel if you guys want to go check out more about the math behind the the backbone of the globe and central angle theorem and all that, how it relates to the positions of the stars and their 15 degree per hour angular descent rate. The occlusion or emergence always occurs at the at the exact distance between the observer and the mountain peak in their central angle, which means that the differences in the measurements here are due to, in reality, the star's true position isn't following their 15 degree per hour descent, but it did have to overcome a mountain peak at that time, and it's not until that 15 degree per hour relationship for that was established could it be observed for the observer. That's why there's a difference in time for the predictions versus the actual time of emergence or occlusion for both globe and flat Earth. It always occurs a little earlier than what's predicted for flat Earth using their 15 degree per hour descent rate, because again, this true position doesn't actually move at that rate, but it does have to overcome an object at that angle relative to the observer with that same 15 degree per hour time component. So that's what's ties both models together, because we share the 15 degree per hour relationship. They just say that it's an angular descent rate relative to the observer, whereas for us there's going to be a lingering effect where it's just going to be horizontal to the ground as it angularly sets for us optically, right? But the actual light source is still angularly above us. So anyway, to participate in that, all the information is shown here. And this is an example recording. So if you can record at about this quality with your device, if you can differentiate the star from the peak there, you're good to go. And then my contact information is down here. We can Cash App or PayPal. How to send me the files is in here. You can use, Google Drive or whatever. Forget the other one, but this is the site I like to use. So you can use whatever you
There's
want.
Dropbox, right?
Yeah, Dropbox. Thank you. I couldn't remember the name. I was going to say Drivebox, but I was like, that's not it. But anyway, email information here, allenspaceaudits@gmail.com. And if you have any questions about occlusions or predictions timings, you want to set something up for a specific location, and whereabouts you're going to be able to do your recording from, let me know, and we can use our Python script generously made by Brian to get some that'll go into Stellarium and get the relative distance and angle for the positions, and then calculate what stars will be at that positions and what times, so you can set up a specific time to go and shoot, because you don't you might be waiting until like 4 a.m. for a star to be at a specific relative angle versus another distance or whatever. So we can look up when the best chances for those occlusions are going to be before you go out. So if you need help with that, just send me an email. All right, back to the Prezie here. All right, and then Shane went over the modern two-sphere model here, and then again, that was just relating these conceptual models that are all just mathematical components based off of an angular descent rate of a true position of where a star once was for an observer. And, according to mainstream history, this coordinate system was given to us, imposed by the king in 1776 by royal decree, that anyone using a different coordinate system where the stars weren't using this 15 degree per hour angular descent rate, you were going to be fined $5. And at the time, that was like equivalent of, financial bankruptcy. So you would be fined per piece of unofficial approved or, unapproved nautical gear. So they wanted you to use their almanacs and their latitude and longitude coordinate system. And then all measurements since then have been based off of those conceptual models. And again, that tracks back to the ECI and the ECI and the ECEF reference frames, which are used for satellites. So they've got this sweet coordinate system with the stars. They've been they've been traversing the ground, making triangles, and then taking zenith measurements of stars and comparing and deflecting their verticals and coming up with gravitational potential models and all this stuff. And then in the early 70s to 80s and 90s, they got the satellite network up and running. And this uses a coordinate system in relation to the center of the Earth to relate their terrestrial sphere models together. And so they continue to have everything built upon this, and they make timing corrections to satellites as they traverse over ground stations that adjust the timing of the clocks on the satellites to make it so that when they send out a signal, it appears position wise that it's being sent from the correct location to correspond to their coordinate system. Oops, Stone. Welcome back, Stone.
Yeah, we blacked out there. Thanks, Elon. But I'm back. We're good.
So let's see here. So anyway, they used the speed of light and timing corrections to keep their coordinate system in check, to make to make GPS internally consistent with their coordinate system. And the mechanism of propulsion or how they stay up and all that is anyone's guess. But mathematically, what they do is they keep the system internally consistent with actual timing corrections based off of transit times of a GPS vehicle over a ground station. So however it works, there's back-end corrections that keep it internally consistent and keep you on the coordinate system, which is the graticule, which people often mistake for a globe. So this is just showing coordinate systems that represent the latitude and longitude system and how it relates to the ellipsoid model and how you're at the center of that coordinate system. And because of that common z-axis alignment, they're able to establish a position on Earth to a position of a star. So they really hammered that point home this season, because that is the backbone of the globe. The globe isn't built on look, there's a horizon or whatever, right? Like that's all after the fact and then turned into the globe. So any observation that you see is turned into the globe. The backbone of it, though, like the actual assertions where you would say, the ground measures flat with respect to the stars, is where they're or versus the Earth measures curved with respect to the stars, is what really solidifies their position. So relating these ground positions to the stars is what makes the Earth a globe, not visually looking out at the horizon. Like a lot of the argumentation that occurs from the globe side, they're like, oh, it should be refracted up, et cetera, et cetera. They can invoke whatever they want because it doesn't matter. What matters is the positions of the stars to define what they're refracting up geometrically as their predicted horizon. That's all defined by the position of the stars. So here's just an overview of that celestial sphere model. Here's that just again observer based. So what an observer would see is one hemisphere at a time in terms of the stars. So if you were at the north, or let's say you're at the equator here, Instead of having the North Pole directly, instead of having the Polaris directly above you at your zenith, it would be at 0 degrees in the horizon. And if you were to start walking towards Polaris and start going towards the North Pole from the equator, you would see that star angularly rise like as an arc as you get closer to it. So this is what you observe. This is what the whole coordinate system is based off of. And like I said earlier, there's a certain angular band where the 15 degree per hour relationship holds, and then any deviations from that are just met with formulaic astronomical refraction corrections to keep that true position bound to a terrestrial position on the ground relative to that observer. And if everyone uses the same coordinate system, then everyone agrees that this is the ground position of the star, even if no such ground position actually exists in reality. Because you're like that. Think about that one for a minute, lads. Like if the star is just moving away from you, and then instead of angularly descending, it just lingers and moves away, versus dropping at 15 degrees per hour, the deviation from that can be represented mathematically as a globe, even though it's not a globe. But you would never know the difference, because all you're basing it off of is where you once saw the star and the current apparent position, which is above the horizon. And if you follow 15 degrees per hour, there's going to be a point where, oh, that should be below the geometric horizon. So the reason I can see it must be because it's refracted up. So that's literally where all that comes from. So it's important to understand how they took that conceptual model to the extreme and then related it to the ground. So again, just showing more pictures of how all of that works in different reference manuals. But it's important to understand the backbone of celestial navigation, because that's what's actually important to prove the globe. Like people often say, like, what's the distance to the stars? Where in your model, and what's the height of the sun in your model, and all that stuff. Well, if you think the Earth is a globe and you're using latitude and longitude to make all that work, you have to be a fictitious observer at the center of a ball of 3959 and make everything angularly descend in a geocentric worldview around you to maintain that. So the angular altitude and following that 15 degree per hour relationship is just as good as any relationship there. I'm sorry, is not just as good as any distance. Using those distances specifically to relate it to that 15 degree per hour angular descent rate is what defines it. And here was the image I was looking for earlier for the transfer of spherical coordinate systems to cylindrical and Cartesian. So just by a mathematical function to relate the angle of transfer to the common z-axis point where they're aligned, all of these coordinates are equally valid at any time. And then so negative coordinates in the system, so that's just what we were talking about earlier. They would predict that the star should be no longer geometrically visible because it's below the horizon, but we still see it. Therefore, it must be refracted up. That's very ad hoc, because in reality, occlusions are a physical process, and when the light source is geometrically intersected by a physical object, the observer can no longer see it. And that's why when we were looking at that spreadsheet, when the central angle drop relative to that observer occurs and it intersects with that peak, that's when the occlusion actually occurs. That's why there's a difference in what we predict using their angular descent rate for flat Earth. So anyway, just relating that in coordinates, you can do that with a negative value for anything below this fundamental plane here that intersects the sphere, and it doesn't have to have physical meaning. It's completely equivalent to if it's traversing a circle above you, but you have a limit of vision, so you're going to see it arc down in the horizon at some point, and then it's no longer going to be visible. Same exact math function will be used to represent that. There's no difference there. And then I was going to have Shane talk about the astrolabe, but Shane isn't with us today, so you'd have to go back and watch the episode where he broke this down and gave an eloquent explanation to the astrolabe. So since he's not here for that, we'll breeze past it here. And this is just from Ptolemy's book here, relating the terrestrial and celestial sphere system, the origins of it. And it's one of the only surviving pieces of literature coming out of the age where everything was destroyed historically, except for this book that tells us that the Earth is a globe as defined by positions of the stars. And there was a cool animation that Shane made here of the positions of the stars snapshotted over a flat Earth, and then the stars just rotate above us, and then perceptually, we see them in an arc, so they descend to the ground. But this is conceptually what it would look like if you had a top-down view of it. You would have stars having fixed positions and rotating away from you on a disk, and then you perceive them arcing to the horizon. But this is what the whole map and everything is all based off of, these positions where these were at a specific time, and then adding 15 degrees per hour to it to have a rotation. So here's the zodiacs here, all configured at the first cusp of Aries, and then just wrapped around the same kind of projection, the same kind of azimuthal equidistant projection here, showing just what that looks like, and then just adding 15 degrees per hour from this is all they did to link it together to the ground. Here's some conceptual sphere models here, and then we have so that was an awesome breakdown of the cosmos and how they relate the celestial and terrestrial sphere models together, and just based off of that observer-centric point of view and that angular descent rate that has to be followed. Then Stone did an awesome debunk of Newtonian mechanics as applied to the moon and the sun and the earth relationship. And we'll take a look at that here in a second after I get some water. So season 14, episode 5 here. Stone using the planetary fact sheet. So NASA, the astronomers in their, need to quantify the positions and weights and of everything, go as far as to say that they know the exact amount of distance and weights and based on the time of year of the planets. So Stone references their actual fact sheet there, they call it. So he can have all the figures to plug into their formula that they use, that Newton once said that he used to derive and prove his theory of gravitation, which is GMM over R squared. So here we're looking at where the figures are coming from in case there's any question. It's not like Stone just made these up. I don't think. Stone, do you enjoy recreationally adding a bunch of zeros to your calculator when you're doing calculations?
Oh, for sure. I like to roll dice to figure out what numbers should be and then go with the dice. I find that most entertaining. Yeah, for sure.
And you have a 22-sided dice, you said?
Oh, I got a 100-side. It's a zoctahedron, Zochta, a zoctahedron. I can't believe it. It's a little blue guy. There's 100 sides on him, just for the people who can't figure out how to roll two 10-sided dice. And
that's illegal.
Work out. Somewhat, yes.
All right, so now that we got all our mainstream numbers, we got our gravity formula. Force is equal to gravity potential times mass times another mass over the distance between them squared. So mass attracting mass is what so they would look at this as like this is the center of the sun to the center of the earth in terms of radius value. It's really the distance to the radius between them, but same thing. Anyway, then their potential falls off at R squared. So we got our conceptual circular orbit here, and we're gonna start applying figures here. And Stone's gonna tire out his 0 key on the keyboard there, inserting all the mainstream formula so we can see what it looks like.
Yeah, to get a new keyboard after that one.
So you can see here that in scientific notation, these look pretty reasonable, 1.98 times 10 to the 30. That's pretty elegant, nothing too suspicious. Then you look at what it is written out and you're like, it's an extra large number, man. But, let's not be intimidated by the largeness of the numbers here.
It's that it's 331,000 times the mass of the Earth. Exactly. Yeah, that's what you have to go with. Suspend that disbelief, you guys. Just roll with it, right? Because this is all just part one. Strap in. It gets way better.
Crazy, dude. Then we take some orbital parameters to get some distance between the moon and the Earth there during its orbit for the orbit around the sun. And then plugging in all the respective formulas to the each relationship there, Earth to moon, and sun to Earth, we get these values down here. And if we were to plot that out on a XYZ axis now, we can start to make a free body diagram and show where the strength of the vector potentials is coming from in terms of magnitude. And instead of looking at it in this notation or these giant numbers, we just break it down to this. We just drop all the zeros essentially. So we got 35,000 relative to 400 and 200 here to make it more relatable to, something that's comprehensible. So then now when we look at that original diagram and we see the difference in gravitational potential there that produce these, perfect circular orbits, it's preposterous. You can see that the prediction would actually be that the moon would spiral out from us. It wouldn't continue doing this forever. And to show that again from another perspective here, the potential difference 2.19 times the potential from the sun to the moon than it is from the Earth to the moon. Just absolutely absurd. And they always tell, like one of the first things they teach you in physics is to make a free body diagram. So like adding up these vector potentials and then showing, where they are over time and what angles they create is going to dictate the, where things are going to be, where the motion is going to make something move based off of the, forces that are acting on it. And so what these vector potentials added up over the course of the Earth orbiting the sun, what would happen is because these pink lines don't all go back to the center here, what's going to happen is it's going to eject the moon from orbit. It's going to spiral out, based off of the sum of all these vectors over the course of a year. So it's really, so for Newton to be like, hey, I developed my theory of planetary motion and Newtonian mechanics, the GMM over R squared, based on lunar motion to test my theory the math isn't mathing out. Stone, what happened? Why isn't the math mathing?
Well, this is just to be clear though, this is 1 month of vector calculations here, day to day.
Oh, sorry, this wasn't even the year.
Yeah, no, this is just the month where the Earth is fixed in terms of the analytical reference, but the physical frame of reference is that of the center of the sun, the very center of the sun. So we're taking a look at the pink lines being the sun attracting the moon, and it's net vector relative to the two centrifugal and two centripetals are really what we're adding here to produce the pinks and the greens. And so anyways, to reiterate, the pink lines are showing the direction of pull on the moon by the sun, and the green ones are the direction of pull on the moon by the Earth. And you can see that they're wildly different from day to day, from week to week, as the moon goes through its quote monthly cycle there around us quote. That you see that the net pull on the moon as it goes both around the Earth and around the sun is far from its actual apparent motion of travel, according to the Globe analysis. That this is all happening 400,000 kilometers away from the Earth. It's 11 degrees out of perfectly circular in terms of its ellipticity. And it's, when you look at the two arrows, the circumferential arrows that are here, the one in the upper right almost looks correct, that the net position should cause the moon, as it moves counterclockwise around us in this diagram, should cause it to continue to turn left. However, when you look at the arrow on the far left, where the vector addition shows that it would actually cause the moon to be pulled to turn right, or to go straight, or to go tangentially at the minimum, it just doesn't appear to do that. And it does it month in and month out. These are the net vectors, month in and month out, roughly, of what the moon allegedly is supposed to be experiencing according to Newton. But Kepler completely disagrees and says, oh no, we need to discard mass immediately, and this is its actual path around the Earth. We're going to ignore Newton, and we're going to ignore the formula, all the mass attracts mass thing, because we're going to ignore mass entirely. And here you see how the motion of the moon does not match the centrifugal, centripetal, vector additional analysis. That's the bottom line, what we're looking at here.
Unfortunate for the heliocentric lads. Quick question. So if their hypothesis were correct, wouldn't to make it cancel out, wouldn't all the vectors be like right angle triangles symmetrically to like make it so that it doesn't eject from orbit? Is that what it would look like if it was as told to us by them?
Yeah, there would be a little bit of non-symmetricality to it, one side of the Earth to the other relative to sun position, the 3 o'clock to 9 o'clock. There would be a little bit of that because they're both going around the sun. But
Gotcha.
It would not be anywhere near this offset week to week.
Right, like yeah, it looks terrible. It's absurd.
Technically, it should constantly be pulling the moon in towards the Earth, a lot on the right side and a little on the left side, but it's not even close. It's constantly pulling it towards the sun because the sun's pull is so much more than that of the Earth's pull on the moon. If mass attracts mass, if this, if that, if the formula is valid, if the numbers are corrected, you know what I mean? That it's it's just silly. It just doesn't add up at all. The math works, they say, but not when you plug in the asserted figures. No, it doesn't work at all.
Yeah, great find. Plugging in the mainstream, or plugging in the significant figures for the mainstream formulas is Stone's favorite pastime. So if anyone has a better formula for him to plug in, like maybe he got it wrong, feel free to send him a correction. You said, how many corrections have you gotten to this?
Well, I've had a couple of assertions about how it's not correct from a lot of people who don't understand frame of reference. And then there was Eric, our beloved librarian, who took the time to ask me even for the spreadsheet that I had put together for this, which I show in the video, and so that he could reconstruct it from scratch on his own. And he did just that. And when he got to the end of it, his conclusion was, yeah, okay, that the math checks out. What we see here is what would it predict? That's what it says. That's what the formula implies. He had no corrections to offer whatsoever. It was exactly as you see it. He was quite satisfied at the end, which is why he sticks around, I guess, inclusively. He's not just a swell guy who digs up books. He's interested. I think that's great.
Shout out to our librarian, Eric.
So the answer to the question quickly is 0 yet again.
Oh, shoot. All right. And then so again, this was all based off of Newton's saying that, the reason he made his mechanics were based off of him being able to solve the positions of the moon using all that, and it didn't work out at all. Like, so after that, we did episode 6, which is the history of Chinese cosmography, which was really interesting because I found out that they were geocentric flat earthers who circumnavigated the world before anyone else did. And in particular, they mapped out the southern stars. They mapped out a star called Canopus, and then they did the angular relationship of 69 miles or 60 nautical miles per degree angular descent. Now, they weren't using nautical miles in their time. They were using a unit called a li, which was an angular slice of the sky, basically an arc second. They were literally using the same celestial sphere latitude longitude coordinate system that is in use today, which I found out that they that the accuracy of that was verified by using an eclipse experiment that we'll go over here. towards the end. But cosmologically, they started out as flat earthers who thought that the heavens were also flat and that you could see forever, and that was in the BC era. And then in the AD era, they changed cosmologies uh, at like 100 AD and became spherical heavens with a flat earth, meaning that they adopted their conceptualization of it was is that you had a spherical limit of vision and that what you saw was a sphere, but their cosmology was still a flat earth. So that's how they adopted their cosmology. They invented trigonometry. They had their own proofs for Pythagoras' theorem, the a squared plus b squared equals c squared. They had their own thing going on. This is all documented and manuscripts from the I can't pronounce. I'm not going to attempt to pronounce it. I was just about to make something up and be like, that's probably it. I'm not going to do it. But anyway, you can learn all about how advanced their math and stuff was. They were and how they were using it in relation to the sky. So the same way that a meter is defined by a terrestrial meridian, 1 billionth of a terrestrial meridian, um, they had the same thing with a unit for a Lee. And it's internally consistent because it's defined by the coordinate system itself that they were using, which was a celestial sphere model. And they made armillary spheres. In particular, they made um, what was it? Equatorial mounted ones, which tell the positions of the stars, sidereal positions, versus the ecliptic ones, which tell the positions of the sun throughout the zodiac of the year. So uh, the latter one was primarily invented and used in Europe. So the Chinese had a completely different one, like time wise speaking, because it's kind of framed that the Europeans sent some Jesuits over to China in the 1600s, and then like they kind of rediscovered slash gave them astronomy and all this stuff. But that wouldn't be possible if they had a armillary sphere that did a completely different thing for their purposes. And then they also ended up making equatorial ones or ecliptic ones as well. So they had like an all-in-one. They had all-in-one ones as well. So they were really advanced in their ability to represent the positions of the celestial bodies and using this conceptual model that was later retold to us by the Ptolemaic story. So they also invented timekeeping methods. So they had water clocks and sand clocks. This is a large clock that would be observed that would be used at an observatory. So they would synchronize, when stars would transit or when actually no, this would be used for what they would do is they would define local solar noon by the positions of gnomes, which are just little poles that they have casting shadows. And as the sun rises and sets, the shadow length reaches a minimum and maximum. So at its midpoint, when it's not casting a shadow, they would start that as their local solar noon. They would start their clock, and then they would have it. Then they would be able to tell the time at night, and then they could relate star transits over the Beijing Observatory to time and things like that. They could start linking celestial phenomenon to time by telling when local solar noon was. So that Gnome system that they had set up, they would have a large pillar at the top of this structure that would cast a shadow down here. And throughout the day, they would place stones on the shadow. And throughout the time of year and day, they came up with tables of the minimum and maximum lengths of the shadows. And then per degree of difference in latitude, they would they could tell by the shadow length what latitude they were at, because every latitude would produce a different shadow length. So they mapped out all these differences and they came up with these tables. So what you could do is you could set up a smaller pole at any location in the world and take a shadow length measurement, and a ratio of the length of the shadow to the pole is going to, and the shadow cast is going to tell you what latitude you're at. So they had this really advanced system of determining latitude independently of anything and timekeeping, and then also based off of that, you'll determine your local solar noon, which you can reset your water clock or your sand clock should it have come out of sync or whatever while you're on your journey. So another interesting thing that I learned was that, so perhaps this coordinate system was wrong, because if you look at the current definition of a Lee, they made it half of the it's been contextually redefined to be half of the length of a terrestrial meridian. So if you were to look at things in terms of like how did the Chinese determine the distance while they were sailing, and yet they would always be half off using the current accepted values, even though same exact coordinate system, same exact internal consistency, but because we now use the redefined version of a meter, which is defined by 1 billionth of a terrestrial meridian, same way the Chinese defined a Li as a ratio of of a terrestrial meridian that they were using for the relationship of the angular descent of the celestial bodies. Uh, they by contextually redefining it, now it appears that they're half off. So when you look at it like that, it doesn't make sense, because the way it's presented now is that the meter is now the true value, right? And then they've gone through to try and redefine what a meter is and all that, but it always ends up being a ratio of the terrestrial meridian as it originally was, and it never has changed. So anyway, using their method of determining longitude for eclipses, what they would do is they had star charts. So remember I said they were taking time recordings of when stars would transit over Beijing, and as the stars would make a zenith transit, they would record, like, was the star traveling with other stars, how bright was it, what color was it flickering, what was its flicker pattern, and they would write down all this information about the star, like, like, did the star take a, did the, was it, did it make like a animal shape, they would have like these abstractions to describe the pattern so that they could be identified. So anyway, when you're out in the field, all you need to do is identify your local time. So they would do that by setting up their sticks and shadows. They would, during the day, they would get their local solar noon time, and then with that they would wait until night, and then during an eclipse, at the moment that the moon emerges from the sun, when the moon fully emerges, or sorry, when the moon just emerges from the sun, they look at what star is at their zenith, and because they've just been indiscriminately mapping stars for years and making patterns and stuff, basically any star that they see they can identify in their star chart, and from that they just take their current time, subtract the time from which the star was at Beijing, and multiply that by 15, and they'll get their longitude. And this method was reproduced in 2001 by 5 people who were, investigating this and trying to reproduce the accuracy of the results. They went to 5 different locations. What was in Melbourne, New Zealand, Singapore, and I can't see the other place, but they went to all these different locations. And basically, at the time of the eclipse, they all viewed the eclipse. They looked, when the moon emerged, they looked at what stars were at their zenith, then referencing in stellarium where that star is at, currently for their time, and then subtracting at where it was at over Beijing once, and then with the time it was over at Beijing, and then they just multiply that out by 15, and that gave them their position within 1 degree of accuracy, which is Tahiti. That was the other place. So that was that's well within the margin of error for celestial navigation. So it still works and applies in an accurate way of determining your longitude if you have the proper references set up. So again, remember, this was all set up prior to the heliocentric model and globe Earth being introduced by the Jesuits in the 1600s. This all took place, between like 0 AD and the 1400s, because when they set out on a sailing expedition and went through the Magellan Strait. This is where they swung by the Falkland Islands to get a zenith measurement of Canopus. It's a circumpolar star, so the highest it gets is 88 degrees, and the lowest it gets is 14 degrees. So they went under it, took a 88-degree measurement, and then started moving away from it. Mapped out that symmetrical 60 lee per mile relationship, 60 nautical lees per mile relationship. And then once they had that, they were good to go. They had different, they had a whole fleet, so they had people at different locations, and then they would wait for an eclipse. And then once they had their eclipse, they would write down the stars that transited, do their references, make it their longitude lines, send everything back to Beijing, and then those guys would update everything, cross-reference the times and whatnot, and update their celestial sphere model, all based off of a single observer and what was once seen at a particular time, and then maintaining that specific ratio of that creates that 1 degree per nautical mile relationship specifically. Because remember, it doesn't hold for the whole angular band from 0 to the horizon. I mean, from a zenith to horizon, it deviates after about 40 degrees or so. So anyway, here's the path that they traveled here, and then this is next to the old Piri Reis map, which is the Chinese added to this map, and this is the Antarctica section, mirroring with the path that they traversed here, and the ice patches and stuff that they encountered and whatnot. And then they came down here, and then went back up, and then went home. But anyway, they contributed to this map here, and they went through the Magellan Strait first. They actually told Magellan about, or they didn't tell Magellan. They told whoever they reported to, when they got home. Word had got to the people that were sending Magellan out, and Magellan had foreknowledge of what was going to be expected when they hit this strait here. And during his expedition, everyone basically died except for his crew, and they were about to do a mutiny. And right when they got to the pass here, he was like, "Guys, I swear I know where we're at. Just trust me." And then he started telling them what they were going to expect as they go through this strait. And because everything was exactly as he said it was, they didn't mutiny him or whatever. And with that, they he couldn't have been the first person to go through it if he was going through it for the first time, and then while simultaneously predicting what was going to be, what the journey was going to be like going through it. So huge contradiction there. Anyway, you can learn more about this from the book, the year China discovered the world. It was a really interesting read. And then that's obviously viewed through the lens of a dude who thinks the Earth is a globe, and he keeps and throughout the book he'll like try and retrofit in the Chinese must have figured it out, and it's like no, like down to the 1800s they were still flat Earth cosmology. So anyway, the Jesuits have contextually retold the story that when they got to the China in the 1600s, that they were basically stagnant in astronomy and knew nothing, and the Jesuits had to correct a bunch of maps for them and help them out and all this stuff. And after teaching them the ways of the globe, they finally accepted it and whatnot. So that's the story as told to us by the Jesuits, but as told to us by the Chinese, it's completely different. And then Shane did a Prezie for the 7th episode on maritime navigation, which is basically showing that, before they had the standardized coordinate system to use and references, they used to just take a bearing to a star and sail in that direction. And you would just dead reckon to a star. And then when when it got to a certain angular altitude, you would reference, whatever other star that's in your catalog, and you would just dead reckon to that star. And through a series of dead reckonings to stars to get them at specific elevations, you got to your location. They didn't have anything standardized, but once you got, where you needed to go, you were, it worked. That's how they used to do it. And that's what the Chinese did essentially. And this was actually, they used to use rumline maps. That's what they would call them. This would be the dead reckoning maps to positions of stars, and then at certain angular checkpoints, you would change position, go to a different star, and dead reckon in that way. And this was like all these maps were contextually redefined when Mercator like reintroduced his projection of this same system, and then they came up with a way to relate these straight lines as a curve along the or a straight line rather when of the rectangle of a Mercator projection. But if you wrap it up, then it would be a curve. But in any case, they contextually redefined all these straight lines to mean curves for the Mercator projection. So that was a huge thing that came out of that in terms of how they navigated. So when did they create the globe? Well, when the Board of Longitude was established, that's when they really started hammering in the need to capture, to maintain to maintain time at sea, because time is going to dictate the specific angle of a star, which tells you, where that star is at that time at that angle. So that's what's relating the ground position of where it is. So that allows you to make your astronomical triangle to tell you where you're at on the terrestrial sphere model by relating the celestial sphere model to the ground. So to do that usefully at sea, they needed an accurate method of keeping time. Now the Chinese had already established water clocks and sand clocks. They also accounted for barometric pressure differences and all that stuff, and altitude different, based on altitude differences. They were pretty advanced water clocks. And then at any time, if it's for some reason got desynchronized, you would just wait the next day, take your sun measurement, and then you'd have time again. But to maintain it with no interruptions, they came up with the pocket watch there. So the history of all that is documented in the Board of Longitude. Shane's done awesome presentations breaking down that whole narrative. But this was part. This is like phase. This is part of the multi-phase series that it took to standardize the coordinate system for everyone to use and getting everyone to accept it. Because otherwise, if you can't keep time at sea, this coordinate system is not useful, and it's more useful to just dead reckon to a star. Oh, it's at this angle now. I don't care what time it is. It's just at this angle now relative to my position. Now I'm going to use this star. Like so, to be more useful than that, you have to maintain time. So again, this is just reiterating that celestial and terrestrial merger here. And then of course we have the episode 8 where Stone revisited the Felix Baumgartner, peace be upon him, high altitude Red Bull jump. Now, it starts off by talking about the camera distortion at the time that he jumped, and looking at the different effects that produced. And it's basically when it's lined up properly, you see that it just makes a straight horizon, and the curvature is like imposed through the lens. So that was a really interesting thing to see when it's bouncing up and down relative to the horizon. You can see when it's angularly aligned to have the least amount of curvature in it, and it it's definitely appears to be not curved in the way that they say it is. So then we got our guy coming out here and he jumps down here, and Stone did an analysis on on the terrestrial features down at the ground from Google Maps and Google Earth, as he's coming down in his descent when analyzing the footage and whatnot. And there was also on-screen telemetry data here, so we have his altitude, airspeed, and all that, so we know when he's in free fall how long his drop is and all that. So I think he fell for, what was it, 9 minutes, Stone? Something like that.
Yep, give or take.
Yeah,
Yep.
pretty gnarly fall. So over that time, the Earth is going to be rotating out from underneath them. There should be a change in position here, and basically, Stone put everything out on a spreadsheet here to account for the differences in speed, for the latitude-dependent rotation, for the time he was in free fall versus not free fall, all the necessary things one would need to dynamically predict when this man hit the ground. Stone included all of that. And then with that, we have our mutually exclusive predictions because the globe is rotating out from underneath him. He should have, based on that time of descent, the Earth should be 6.36 miles to the west of him. And he actually ended up landing 43 miles to the east. Am I reading that correct, Stone?
Yeah, pretty much all of it. The spreadsheet actually didn't compute his fall time. It computed his rise time because that was 158 minutes long. And as he's rising, as R is increasing, that's how he loses position against the Earth, which is allegedly spinning at 680 miles an hour underneath him. So if his tangential velocity remains the same as when he was lifting off the surface, because he's in a balloon allegedly just going straight up unpowered with near zero wind at the surface, necessarily in order to be able to take off safely, he went up for 158 minutes. But somehow 158 minutes later, he jumps out and falls for 9 and lands 40 odd miles to the east, when that is the direction the Earth is allegedly spinning faster than him underneath him for 158 minutes as he was rising, such that he should have jumped out and landed to the west, but he didn't. He's off by 50 miles net. And that is exactly what this is about. Yeah.
Yeah. Thank you. I missed that part on the, this actually the whole descent or the whole ascent time plus the descent. That's insane, dude. 43 miles in the opposite direction. And then, so I didn't cover it in the graphs here, but the mainstream, it was recently commented that the explanation was that we forgot about how wind works. So wind actually is the culprit for high. So guys, the Earth would be a globe, but the reason that it disagreed with the globe measurement and agreed with what a flat Earth would predict was because of the wind. It's making it appear that the Earth is flat and stationary. And Stone, if I'm not mistaken, you did a follow-up on this where you went back and looked at the wind data and all that. Was there a follow-up to this?
Sure did. Yeah, it was a response to the critique that I received about how wind exists and yeah, that kind of thing, where we understand that he actually, total rise time, total altitude was to the tune of 127,000 feet. However, convective cells only form and operate and move around and exist up to about 40,000. So when there is no, even on top of that, there isn't a lot of air to push him when he's up there. It's got to do so much harder job to get him to go 43 miles after he's so far up for the, for the last 2/3 of his rise to go up, geometrically speaking, as R is increasing over those 158 minutes. There is less and less wind to actually do the pushing. On top of, well, geez, guys, if we're talking about 680 miles an hour or whatever to begin with at the surface, just for the wind to appear to be stationary, how much faster does the wind have to be going than the Earth? What does its total speed have to be in order to push him to the east? They don't have a lot of answer to that either. It's just something they don't talk about. They just kind of breeze past it, pun intended.
Nice. Yeah, awesome Prezie on that one. Just such a simple and elegant, should be this way, ended up 43 miles in the opposite direction.
Yeah, in part of that critique, it was asserted that wind is a myth that I quoted in my review during that presentation. Winds of up to 200 miles an hour and some. And in the critique of my review of that presentation, I was accused of just making all that up, that it is a myth that winds travel that fast and that kind of thing. So again, in the review of the critique, I provided the actual screenshots where I showed that in the review, that they were actually present during the critique, but the guy doing the critiquing doesn't understand what he's looking at in a wind diagram and could not see that the velocity was actually evident in what he was presenting, that he was asserting was a myth simultaneously.
I remember that. It was in a different metric. Yeah, that's unfortunate.
Yeah, it was a bobwinds.com shot, upper atmosphere selected, where there's not a lot of wind up there, but what is up there somehow seems to be moving at about 225 miles an hour. And as that was on the screen, the critique coming back was that I must be making that up, that I created some mythical thing known as a jet stream wind velocity. It was just amazing. Yeah.
Absolutely absurd. All right. I just realized we're approaching 2 hours here. I'm going to try and breeze through the rest of these.
Yeah, I've been watching the clock there, Alan. You're really covering the detail here today. There's a lot of material.
Yeah. Okay, so we got the Redshift Prezie. That was our 9th episode, going over Holton Arp and the discrepancies that he found in the mainstream model. Shout out to our boy Holton Arp.
The persecuted one. Yes.
He who must not be named in the mainstream. So we went over the how they relate these vast distances in their conceptual model with the speed of light. So you can kind of think about it like this: if you were on the surface of the sun and the light propagated for 1 second, it would get this far away. So they turn that into a unit of measurement, describe it over more time, you get more distance, and that's kind of the backbone of how they relate everything conceptually. And then they came up with the astronomical unit, which is defined by the distance in kilometers from the Earth to the Sun here. And then if you were to move away from the Earth and Sun relationship here, at the time that they angularly converge to 1 arcsecond apart, you would be 3.26 light years away. So in terms of light year distance, you would have to travel that far away to see these two converged. Like if you were thinking about a car's headlights and when it's closer and further from you, when you can see one headlight versus two, to get that relationship there, you'd have to be 3.26 light years away. So then using that unit of measurement, they came up with a way to describe brightness at different distances. So the distance you see isn't, the brightness you see isn't the true brightness. You have to use this parsec reference of distance to relate what an observer would see under these conditions. And then using that scale, which is logarithmically inverted and negative, which makes no apparent sense, is then used to describe the visual magnitude versus the absolute or the apparent magnitude, which is what you see, versus the absolute magnitude, which is the calculated version based off of a, you guessed it, fictitious observer to bind everything together. So this hypothetical person that exists at a distance of 10 parsecs away would see it at this bright. So by doing this, they can turn any star into whatever distance they want out of it with no physical meaning, because it's just going to be related to what would hypothetically be, and that could be whatever they need it to be. Then we learned about spectral emissions. So when looking at light that's being emitted from a light source versus light that's being emitted from a source that's going through a medium of gas or something like that, some sort of particulate matter that it's interacting with, you will get a different reading in the spectral analysis. When you split that light into a rainbow, you will see that it is either missing components. Those are absorption spectrums. That means that the frequency of light matched the frequency of the material that is in the that it was like propagating through, and then you get an absence here because it got canceled out. And then on the emission spectrum, you'll see that the other things were canceled out, and but the spectrum that was emitted was the frequency of the elements that basically blocked out everything else. And then a continuous spectrum, do you see, if you split the rainbow, you get a nice continuous gradient with no hard cutoff points or no hard defined absorption or spectrum lines. And the sun produces this unique spectrum, this unique continuous spectrum. And from my understanding, everything else in the sky does not produce that continuous spectrum. They have these absorption and emission lines. So that's really interesting, because no other, we're told that the sun is a baby star. It's an inadequate star. It's the smallest star out there in the sea of stars. But it produces this unique spectrum that's unlike anything else in the sky. So that's pretty cool if you're into things that are unique. um, with the relationship of spectral shift and Doppler shift in relation to velocity, they turned that into a linear relationship for velocity and distance. So now any sort of spectral shift can be interpreted from Doppler shift into a distance. So now they establish distances based off of red shift and blue shift. So the frequency change in light now, not just the absorption spectrum, but just the frequency change from what the spectrum would be with respect to lab settings. They take the difference, which comes out to be a V over C relationship, which is a linear velocity with respect to C, which, don't tell anyone, implies an ether preferred frame for the velocity to be relative to. So it's saying that light, or the velocity relative to light in its own frame. There's what they use to determine these velocities, but they don't want them to be physically meaningful, so they make it, all relative to the expansion between us and what we're seeing, and not the actual object itself moving in space that's expanding between us. And this is all, of course, resulted from Big Bang cosmology, where there was once an explosion out of nothing, and then everything started to slowly congeal as time went on. And one of my favorite things about this presentation was this redshift hypothesis from YP Varnishi, where they have 57 quasars that are visible from the Earth, and you can, distance-wise, if you were to map it out in their model, it would create 57 concentric shells around Earth, only visible from our perspective. If you were on Mars, if you were on the Andromeda Galaxy, if you were anywhere else in their conceptual model other than Earth, you would not see these stars. So he proposes several explanations to explain it, none of which pan out. And the third explanation is, of course, to abandon the cosmological principle and special and general relativity, because none of those coordinate systems that describe mainstream cosmology that tie all this together are physically meaningful. And then he ends on saying, nah, maybe we'll just throw out our interpretation of redshift, which was proposed by Hubble here, which establishes a linear relationship between velocity and distance. So he's saying maybe they can throw that out and ignore it and keep their conceptual model going. And then for presentations 10 and 11, Paul from Plain Reality came by and showed us about refraction and how the horizon changes throughout the day, and it's an apparent effect due to optics and refraction rather than geometric Earth curvature. Went over a ton of material there and some awesome diagrams showing Dave and Sally, or I'm sorry, Bob and Sally. And one of my favorite diagrams that came out of this was here, and you can see as these squares get closer to the horizon, they change in apparent size, even though they represent the same length there. So this is an important aspect of optics in terms of why things get smaller at the horizon and how that information loss causes bottom up obstruction. And in relation to, ships and boats and even clouds, doing the same effect, but in the sky is it's just an effect of how we see. So this was a great 2-part series by Paul. Highly recommend checking that out. And he breaks down the mechanism of refraction itself, gets super into it. It's great Prezie. Did the history of wave invariance here for episode 12, which was awesome because it turns out that relativity, which claims that the speed of light for a moving observer is always the speed of light and it's never measured as anything different. But then it turns out that those equations were actually just derived from from an elastic medium to describe Doppler shift with respect to said elastic medium. And it describes the basically, like, mechanistically, it's describing the timing and spacing difference for the frequency of waves rather than the difference of reality, like time and distance, for link contraction and time dilation. So instead of reality contracting and compressing, it's just the actual wave as seen by the observer who's in motion relative to it is going to measure a frequency shift that's proportional to that velocity. So anyway, it was cool to learn about that. So throughout the history of light and ratioing velocities against it, they tried to support their model with what's called stellar aberration. And then after that, they started to do experiments where they would introduce a manipulation of an independent variable to change the dependent variable, which in this case would be the deflected angle of the starlight. And they didn't get any sort of deflections that would correspond to the Earth being the cause of the motion. What it implies, if there's no angle change, is that the starlight already comes in at that angle. So they went through a series of, trying to figure out that whole situation, while at the same time deriving interferometric principles that would describe the velocity of light through a moving medium and how that would change the interference pattern, and how that also corresponds to the frequency change in light based off of velocity, which is how a radar gun works. It's actually called a beat frequency. So for every frequency emitted, it's going to change proportional to a velocity component, and you could ratio that out to whatever velocity you want. It's going to change that original frequency proportional to that velocity. So by getting whatever you send out, a beat frequency table can be referenced to tell you what velocity component that was. And that's what this gentleman established here with his spreadsheet here. We can see different velocities and different beat frequencies that correspond to those, starting with the original emitting frequency. So all these principles, of course, derived in the early 1800s, and then an interferometric measurements showing the velocity of light adding to the velocity of water adding to the velocity of light here in interferometric readings. And this doesn't only occur longitudinally when the direction is going with the flow, but also transversely when you're perpendicular to the direction of motion. There's always an interference pattern that is in the same direction, irrespective of the rotation of the transverse motion here, which is a huge significant find, because if relativity theory were true, then the displacement of the interference pattern should be dependent on the direction of the rotation of the transverse motion, but it's not. So that's pretty damning evidence against relativity theory. Only an ether theory would predict the transverse motion like that to be there to cause that difference. And they knew about all this experimental evidence in relation to angles of light and motion, because in 1862, Foucault did experiments doing the same thing, showing the angular change with a rotating mirror when adding water. The velocity of the rotating mirror dictates the amount of angle that is produced when that's different from when the mirror is stationary. And then, of course, deriving the speed of light under physical vacuum constants. So the inverse of the square of mu in epsilon, which is the magnetic and electric vacuum constants, gives the velocity component of light. And then Airy's failure, measuring no angle change for the velocity of Earth going through everything. But more importantly here, we have the original source of the Lorentz transformations, which can be done by just algebraically rescaling the forms to the longitudinal form. So right now they're in the transverse form, which doesn't lead to link contraction in the x direction. But anyway, if you multiply that out to rescale it, you'll actually get the modern Lorentz transformation, and even Lorentz noted that. And in this really cool experiment where where gas was deionized and then reionized so that it would become a moving photon emitter, essentially a moving light emitter at quote unquote relativistic speeds, they were able to measure frequency shifts that are proportional to what these equations predict with respect to an elastic medium, rather than no physical purpose at all, which is what relativity would predict. So it was awesome to go through that history and make that connection to these equations, which are said to be relativistic, and then realizing that Einstein never actually derived these equations under the postulates of relativity, meaning that the speed of light is independent of the state of motion. To derive his equations, he actually used motion relative to a stationary clock rather than a stationary medium, and derive the exact same thing but different. So anyway, that was just a crazy history. So there's no new interpretation of physics. There's no etherless physics. It's always been physics with respect to an elastic medium as described by these equations here.
So what Lorentz had to do there was essentially fudge it, right?
What Einstein had to do was fudge it. But yeah, just had to fudge it up. And then so Stone gets into his thoughts about electrical engineering, or I'm sorry, how light propagates essentially in
Electromechanics. Yes, indeed.
electrodynamics here in episode 13. And one of the important things that was described was breaking light down into three components. It was induction, and I forget the other two components, but it had to relate to how it propagates through space using counter space as the mechanism to tie all three of the components together to make an EM wave. Is that kind of more or less what happened there?
Well, I covered induction, and then I covered electrostatics, and then I covered a little bit of ether and counter space. And then I covered some, like you see here, some toroidal geometry applications of those three in a commutative way, and addressed, among other things, the jet stream in the process when we got this far in the presentation. Yeah.
Yeah, my favorite part of the Prezie was the jet stream relationship, the physical movement of the jet streams being caused by the ether, and then that model, that toroidal model you made is, dude, it's awesome.
And thank you. In the water in the air that is supposedly up there doing the wind thing is diamagnetic. And that's how you're getting the acceleration in the field.
Yep. So awesome. So yeah, we went over the physical, mechanical properties and how it interacts with material matter. And so that was a great Prezie on that. So we learned about EM propagation, induction, statics, and magnets, and also jet streams and how it relates to diamagnetics and how that's creating the motion through the force lines of a toroidal field. Awesome. Then for episode 14, we did the celestial theodolite eclipse edition, which was a new application of the celestial theodolite principles. So taking the angular drop relationship of 60 nautical miles per degree, we take an observer at the equator, we move the sun, or well, in this case, giving a North Pole example, for the sun's actually at the equator, so that's not going to make sense. But anyway, if you were to watch the sun angularly descend from your zenith, it would follow a 60 nautical mile per degree relationship, and you can multiply that all out to get a radius of 6,370,000, which is about Earth's radius. So deriving that all from that angular relationship of the descent of the sun, using the coordinate system of nautical miles, which is just a ratio of a circle in this coordinate system. So by using all that, you can get this relationship here, which gives you a radius value. And then you can do the same thing for the moon, but it actually follows a slightly smaller radius value. So if you think about the sun being at one that follows 60 nautical miles per degree, and this one would follow one that is slightly smaller at 59 nautical miles per degree. So to kind of put that in quantification, it seems like a small amount, but if you were to think about it in terms of how far angularly does it have to descend into the horizon before it's no longer visible, the sun would have to go all 90 degrees, and whereas the moon would only have to go 88 degrees. You can kind of think about it like that. So this is kind of showing the relationship here, like the mathematical equivalence of a circle and a hemisphere of vision. Because what they'll do is they say that the Earth is a sphere and you have to use spherical trig, and in spherical trig, the sides of a triangle add up to over 180 degrees. But if you do a Euclidean projection, 2D projection using central angle theorem of a sphere of a radius that they give us, the mathematical difference from what they predict is nothing. And actually, you have to use Euclidean 2D projections anyway to add things like surface elevation to the sphere relative to the center of it, because they only predict like surface area of a sphere, a spherical trig. It doesn't predict like angular elevation, it doesn't predict elevation like that with respect to the center of it. So anyway, you have to merge the two anyway, so they're inherently equivalent and fine. Although the triangle situation does lead to, one leads to 180 degrees exactly, the other leads to 180 degrees plus, but they both have to be used to make any of this useful on their model for things above sea level and whatnot. So anyway, this is just showing that, and based off of the eclipses, what we have is this relationship where, for them, they would say that the center of the ball is creating the distance on the surface of the sphere, which is relating the angular change in the positions of the stars, whereas we have the same position, but we could use trig to calculate the actual altitude, and what we would get is this would become, instead of a radius, this becomes the physical altitude of the celestial sphere. So showing the equivalence of the two systems here, that's what we're looking at. So all these angles are all equivalent and they all produce the same result as if you were traversing over a sphere with a radius of 3959, or if you were or if you were traversing over a plane and using a coordinate system derived from the angular change based off of optics, where the sky is curved. That angular change based on the sky being traversed on the ground is directly equivalent. That's what the math is showing here. So based off of taking the angular relationships derived earlier from the sun and moon relationships, what Brian can do is multiply or do some trig over an eclipse shadow and derive what the elevation of the sun would have to be for the moon to occlude it based off of the rise over run using the elevation given here that was derived from the angular change, and then just using this as a physical altitude. So if the Earth were a globe, as you calculate the rise over run, or no, the tangent function to calculate what the altitude would be based off of the angle and the distance of the shadow length, you would get a curve like this where over 7 million meters, the length of the shadow length, these observers would start plotting out an elevation change. So it would look like this. There would be 4 million meters of curvature over that 7 million meter shadow length for the observers as you plot out that change. But what Brian calculated for the elevation of the sun relative to the elevation of the moon, so putting that up at its value, that was, what was that for the moon? That was for the sun. For the moon, putting that up at 6,274,000. There's almost no change. And remember, it goes back and forth a little bit. So going back and forth, there's no elevation change over the entire duration of the eclipse. So that's a pretty fascinating in terms of relating how their derived conceptual model is based off of a physical elevation change, yet you can derive the same thing with no elevation change, and just relating the position differences optically is what their whole coordinate system is based off of. So that was an awesome Prezie by Brian. Then in episode 15, Bambi came in and told us about terrestrial refraction being a line of sight phenomenon, and he gave the example of the Chicago skyline there. And we went over different aspects of refraction and how the image is formed. To create image formation is contingent on a boundary interface, which means you have to have a sharp medium change for the image to be projected on so that it can appear to have convergent lines for the observer to observe it lifted up and that also requires geometric alignment. It can't be like lower than the object, as we're going to find out from a later Prezie that Bambi followed up on. But going through that, he gave different examples of how a second medium has to be introduced to get this looming effect, to get this lifting effect. And it's always like, in this case, it's this crystal prism here that's introduced to lift the house up over the thing that's not even geometrically occluding it. It's occluding it for the observer and then lifting it up on this project, basically giving it a place to be projected on, allows the observer to now see it. So this isn't analogous to what we see because on Earth, they say that the Earth has a homogeneous gradient, and the homogeneous gradient doesn't produce a boundary layer for an image to be lifted on. So he goes over the difference for examples that are given as proof that refraction bends light. Well, this is bending a coherent laser beam, which is collimated and at a specific wavelength for it to be focused. Now it does bend, but this isn't the same as image formation. So to get something like this, where like a silhouette is being projected, so relative to the observer, this image is actually, like, in reality would be tilted away from them. But they see it directly, straight up. It's absurd to think that the absence of this is being lifted up over to create the exact sharp silhouette of what it would look like if the Earth were flat and the sun.
Keyword being sharp. Yes, totally.
Yeah, the sharpness destroys it. So yeah, that was an awesome Prezie by Bambi. And then we get into the distance of the sun from Shane for episode 16 here, which was great because they end up using that fictitious observer again to link that radius value, which describes the angular descent rate of the stars, to create the 15 degree per hour relationship for the angular descent. They use that radius value to then define the astronomical unit. So the distance to the sun from the Earth becomes a ratio of the radius itself, the original Earth radius, by making a triangle with Venus during the aphelion intersection points, and then assuming that Venus is the same size as Earth and drawing a triangle from the two, and using a little central angle theorem, they deduce what the physical distance would be as a ratio of Earth's radius. So they have that linked in. Goes over the history of how all the information we ever have is the angular size of the sun. Getting a distance requires knowing an additional component of the triangle to solve it. So using the distance and circumference value, just changing what the radius of the sun would be, they would get different values there, and that's how they link the whole thing together. Or went through the history of getting more and more progressively accurate, but then they all settle on this 93 million mile number. So they just need to physically confirm it, because otherwise, due to scale invariance, if you change one of the factors, whatever you change the other factor that you're making your triangle with, if you scale that by the same factor, everything will change proportionally. So if you change the distance and the circumference of the sun, or what you're looking at for the angular size, then everything is going to change proportionally, and you're still going to see it at its 0.53 degrees in angular size. So that rescaling factor and proportionality doesn't make their model mutually exclusive. They need to tie it to a physical measurement. So they tried to do that with radio wave measurements here, and Stone pointed out that there's no y-axis component for the magnitude of these measurements.
There's no unit of measurement for the magnitude. Yes, for the y. Yeah.
Yeah, because what we're looking at here is just noise, and then we don't know how much more noise the measurement is versus the regular noise. So they've like left it obscured, and all the measurements for these experiments like this are left like this. We don't have any sort of way to determine the noise, but they swear that within this moment of noise, there was the intersection and all that. But the big takeaway from this was finding this document from the Jet Propulsion Laboratory, um, where this guy says the fundamental constants of the Earth, consisting of elements of its orbits, the mass, constants specifying size, shape, orientation, rotation, inner constitution, and the velocity of light, comprise the system of astronomical constants. The group of constants has been called a system of constants because it's comprised of a model of Earth and its motions. The interpretation of the astronomical observations depends on this particular model. Furthermore, because many of the theoretical relationships involving several of the fundamental constants, some of the constants are necessarily systematically related. De Sitter in 1938 wrote, an ideal system of fundamental constants would be one of which those are theoretical relations were satisfied rigorously while the adopted value of each individual constant agreed with its observed value within the limits of uncertainty of the latter. This ideal has not been realized even to this day. So all of these measurements are all of these constants used to even assert this relationship of size to celestial bodies and this and all that within their model is all a ratio that's independent of one another. They're not independently confirmed.
They are perfectly circular.
Yeah. Yeah. If you were making a spreadsheet and you changed one of these values, they would all brick because they're all interdependent on one another in this. And that is not ideal, as De Sitter correctly stated here. And then here's us all having a good chuckle at that after we learned that that they were all a ratio of one another. All right. So then,
I look like I stubbed my toe in that one.
All right, so we have episode 17, which is Stone's ILS experiment. Well, now this one is awesome because using plane radar, we have their three-dimensional position in space. Using their glide scope, here's what that looks like. Using cross intersections of radar that's being sent out at different angles as the plane's flying through it. We have their exact location, and so for distance-wise, we know where they're at relative to this radar system. Using their internal glide scope, we have their altitude based off of barometric pressure. We have their angle of ascent. And we have their distance, I believe. What was the other thing? What am I missing from here?
Yep, distance in the lower left.
And their speed, it looks like, too.
Yeah, speed on the 9 o'clock position on the far left, speed at 145. Distance at 7.4 nautical in the lower left corner.
Got you. Yep, so
right?
we have... Yep. So we
and
have
also the rate at which it's dropping, where is that 800 feet per minute in descent on the far right, past 3,740 feet. Yes, indeed.
Yes. So using this glide scope, we have all the necessary information to compute what the globe predicts versus what flat Earth predicts in terms of where this plane should be position-wise, and not just position-wise relative to the radar system, but also in elevation relative to the ground. Because on a globe, the further out they are relative to this radar system, the more drop over distance there is, the higher in elevation the plane should be. And what Stone measured out with this, because he actually proposed this experiment be redone where they do a holding pattern over a specific section, so that once they get leveled out directly, they can just fly over consistently. And if the Earth is a globe, they should be measuring a constant change in elevation as they complete their circuit over this distance based off of the Earth curve. But what would happen is that there would be no elevation change. Now, how do you know that, Alan? This was a proposed experiment. It hasn't been done yet. No, you're wrong. Stone has a pilot that made like 3 attempts to get this data correct, so we could read the glide scope correctly. And after we got the correct data, Stone plotted out the differences for what they predict, and the plane is lower than what the globe predicts every time by like 140 to 200 some meters, I think. And then distance wise, it ends up being 1 nautical mile closer than what the globe predicts, if I'm not mistaken.
You did a lot of melanging there. The earlier data was actually a closer point at intercept at only 10 nautical miles from the tower, the original data from a couple of years ago. And the difference is that data, when we were approaching and getting a reading measurement at 10 miles from, the plane is still in descent. Like we were seeing that he was dropping 800 feet per minute in that first one, showing 0.35 degrees per tick in the glide slope resolution. What we're doing here is, like you said, leveling off, and we're approaching the point of intercept at a single altitude. And it is a question of the trigonometry between the tower shooting up at 3 degrees and the level line of the plane which is flying, and exactly how far from the tower those two lines are going to intercept. What will the altitude be of the plane, and what will the distance from the tower be? And those are the things that if we are to compute, like you see in these two scenarios, that on the altimeter, if the reading is going to be the same at 6360 above runway altitude, that the point at which we're going to intercept that 3 degree line is different for the two scenarios because of the globe drop-off, like you see at the bottom at 8 inches per square mile. That there's 318 additional feet of drop-off there that are going to cause the plane in the globe scenario to appear lower relative to the tower, which is the fixed component of this analysis. The tower is fixed, the angle is fixed. It is a question of, given our fixed altitude, what is the distance at the point of intercept between the two models, and they're about a nautical mile apart, like you see here, 20 and 19 nautical miles apart, and that's how they add up. So yes, I went from here and plotted out both an animation we were about to show of what it looks like to fly those two scenarios simultaneously, where they would both intercept that 3-degree angle on the right side of what we're seeing at the same moment, at either after the end of 94 seconds or the end of 79 seconds, that it takes them both to travel between 2.65 degrees and 3.0 degrees relative to the angle of the tower, which is fixed. I hope that makes sense. That was a long ass explanation, but that's what it's about.
Yeah, no, it's awesome, dude. And it's like, it's basically mini Battle of the Beams. They just did the same thing in Germany, but with a bigger radar.
Yeah, it's a fair bit. Yeah, it's no longer, gee, can the plane receive the signal that far away? Now it's, okay, well, we've put the signal up in the air. Where is the plane when it intercepts it, rather? Where are we in physical space relative to the tower when we hit that thing? And that is a function of altitude. And if there is globe drop-off, there's a 318-foot difference between the altitudes of these two planes. And if the lower one is flying according to globe geometry and the top one is flying according to flat geometry, like you see here, then their intercept points of that 3-degree angle will necessarily be at two different physical points in space because of the altimeter reading being the same for both. So that's what this scenario here shows in real time, so that you get a grip on just how long it takes the pink diamond to go from one dot above level 0 intercept point and the actual intercept point across the center of the gauge in both scenarios. And it takes quite a long time. So it's not like you're going to blink and miss it, if you know what I mean. That's part of the foolproofedness of the plan, is that it's real easy to see when that point occurs and just mark down, okay, that's the second. That's about as precise as you need to be. That's the distance to within 1/10 of a nautical mile. That's as precise as you need to be. And there you go. That's the data. It's a real easy thing to fly. And I will announce that I already have one submission from that same Vietnamese training pilot, the commercial jet pilot out there. He has already sent me one recording of an approach intercepting at 20 nautical miles away. And I'm not going to talk much more about it because the difference between this scenario and the one that he flew was that he was actually still flying descent. He was still dropping at 600-800 feet or per minute, or I forget what the figure was, that he was on the approach, the 3-degree line, before this point of intercept that you see in the diagram. And that's the difference between the two. I want to get absolutely sure that this is the pattern that's being flown. So we're continuing communication, he and I, and
Nice.
Still looking for more data on top of that. Just give the Globies absolutely nothing to object, nothing to talk about. You know what I mean? The data will just be so irrefutable.
Irrefutable data is one of my favesies.
That's the goal right here. So I'm putting the call out now to more of you, especially commercial pilots who are out there. All you need in order to make this happen is be on this descent at, say, 25 miles or greater out. But when you hit 25 nautical miles, drop faster. So by the time you get to about 23 nautical miles, you're already at 63, 60 above and flying level to this intercept point, which you will eventually cross. And after you do, increase your descent until you catch up again with that 3-degree line of descent, maybe 18 miles from the tower still, which is all easily fudgeable in a commercial plot, in a commercial flight plan, that the passengers may not even notice, although you could announce that that's what you're doing and they would appreciate the maneuver itself for the fact that you're gaining data in the name of science. But the point being that if you were indeed a commercial pilot, starting the scenario at 25 nautical miles away, over descending until about 23 away, hitting 63, 60 above at that point, flying level in approach to 20, intercepting the 20, and then resuming your descent, you would easily catch that 3-degree slope again in another 10, 20 seconds, in another mile or two, and be on your way to the airport just like nothing happened. And you would be able to get this data easily and confidently, which is far more important.
Well, hopefully we hear back from some pilots. Shout out to the one who's helping you out there. That's awesome.
Indeed. Indeed.
All right. So in episode 18, we got into gravimetry. Shane went over the measurements and how they, without a coordinate system to relate them to, they don't prove anything. So a lot of people say that there's latitude dependent variations of gravity that's measured. So little g. So they have different instruments to make these measurements. But what we found is that they take the measurement and then they fit it to the coordinate system rather than having actual latitude dependent measurements. And then the scale at which these amounts fluctuates is extremely small. I think it was 300 thousandths of a Gauss or something like that. What was it, Stone? Of a Galvin,
The gal itself being a
Yeah.
100,000th of g of a meter per second.
Oh, 100,000th
Yeah,
of it. Yeah, just some
right.
absurd
Right. So we're
ratio.
talking about tenths of a meter per second. Yeah.
Yeah, we're talking about like literally nothing, but because it's color coordinated and there's like depth to it, you might be led to the conclusion that like, oh, there's less happening here and more here. Not that you would ever notice or matter. And then here's Neil deGrasse Tyson's retracting all of his statements about all the times he said that because the Earth's a globe, there's latitude dependent measurements. But now, because of calculus, he's determined that that's not true because you can actually cancel out the gravitational potential difference between a ball rotating and the latitude dependent variations or whatever. So, anyway, in long story short, calculus. Then we move on to terrestrial refraction for episode 19. Vanby took us into episode 19 for in the lab demonstrations of of refraction effects, because the Globe labs were not satisfied with his previous presentation and they were out to prove him wrong and provide some examples and whatnot. So we have a couple examples here. The laser and fish tank, again, not analogous because it's not image formation in particular. This one's introducing a second medium. This is the most close because there's no other medium, but they're using a hot plate to change the gradient here, so we can see what happens. We get this blurring and compressing here, but we don't get any lifting above anything or anything crazy like that. So that's a pretty cool one. And then in this scenario down here in the bottom right, this is the famous video where the guy pours some propane or something on a tank here, and that causes it to cool.
Yeah. Liquid
What was it?
butane.
Oh, liquid
Yeah.
butane. Thank you. I knew it was something. I was like, propane? No. Yeah, he pours out butane on there, cools the surrounding area. The temperature gradient changes, which lifts up the light for the observer down here that's being blocked by this tank. And you can see this red Play-Doh that's wrapped around a spray paint can or whatever. Now, normally when there's no butane being spilled on top of this, you don't see the red here. Now, Vanby points out that this blue and red Play-Doh isn't geometrically obstructed by this tank object here. It's actually on a platform, on a milk crate or something that's lifted up above the tank. Only for the observer is it occluded like optically relative to where he's at. But in other words, the light rays emitted from the red Play-Doh are in reality, overcoming the tank here. So changing their directional path with the medium change allows the observer to see it. So Vandy was hypothesizing that if you were to actually have a scenario where this Play-Doh was lower than the actual object occluding it, then you wouldn't be able to lift it up. And he goes on to experimentally verify that. So here's a close up of that Play-Doh being lifted up. And then when there's no refractive, you don't see the red, you only see the blue. So to test this hypothesis out, to make it more analogous, because this isn't even analogous either, because this is an object that's separated in distance from the object doing the occluding. In this scenario here, he fixes a magnet to a can, rolls it away from the camera, and as you can see, when it changes in an elevation relative to that, the horizon created by the can, when he introduces the butane, the magnet doesn't appear over the edge; it's geometrically occluded. And then so this is to kind of show what he's talking about in terms of the elevation of this being higher than the object that's occluding relative to the observer here. So these light rays are being, cast out in all directions, but relative to the observer, he's not going to get them because it's optically occluded for him. But when you introduce that medium, those rays get bent down, image formation occurs, you see the apparent image under the Play-Doh. So analogously, to make it representative to what should be occurring on a globe and whatnot, he comes up with this configuration where the Play-Doh is actually geometrically under the thing occluding it, but all lined up on the same line of sight. So if we had butane here, is it going to again lift it up? Well, no, that's not what happens at all. So here's a diagram of what Vanby's setup was. We have the object geometrically under the object occluding it. He adds butane to it, and there's no, it never gets lifted up. So you can check out the video of him doing that all in there. But that's what we're looking at here. So the idea that refraction lifting things up is a physical explanation to explain observations that falsify Earth's radius, where an effective Earth radius has to be introduced based off of a refraction coefficient to be applied to every observation, turns out to be an invalid hypothesis mechanistically, because when you have a geometric obstruction for your occlusion, there's no amount of refraction is going to lift that light over that object. Especially
certainly not naturally. Yeah.
Yes, especially not such that it's going to allow image formation and all that. So, all right. Well, that concludes the recap there. Sorry, I went on a little long. I didn't realize I was giving full recap summaries of each
That
one.
was quite the ride, man.
but yeah, it was a great series, great season, man, and just really hammered home that celestial sphere model, and that doesn't represent reality in any of the measurements that are being taken, and data actually has to be retrofitted to it. So. All right, we will see you guys on the return in March. Enjoy your holidays and spring and all that. See you guys on the return.
Yeah, thanks to Shire for tossing up my Rumble Addy in the chat there. I wanted to address that just for a sec because
Yeah,
it's
absolutely.
just the matter of the migration itself. Like back on BitChute, been there for 4 years or whatever. I got about 1,000 subs. Everything's hunky, but don't want to use them anymore. The new account being the Rumble account. If I think I'm well over halfway there, but if we could get that up, you guys, to over 100 subs, then the URL will actually change. It'll be to /me or /fe amount of stone instead of that weird alphanumeric string that Shire graciously posted for us minutes ago for my channel. So yeah, just a heads up. That's something I'm looking forward to in terms of ease of reference. If you guys could help out, that would be great. And we could announce Tuesday night.
Support the boys on Rumble, Flat Earth, Man of Stone. And then, yeah, we're gonna have a trivia night on Tuesday, like you were just saying. And if you don't want to join the Discord, you're a little shy, you don't want to participate, you can participate in the chat and still have a chance to win an Ether Cause hat and T-shirt. So.
And just before that, you're planning a kind of a recap on Discord for Tuesday night.
Yes, and it'll be a much shorter recap.
promises.
It'll be a much shorter recap.
In between that being the first thing and trivia night being the third thing, the second thing that's right in the middle is going to be a video release of mine that you guys might want to come by and get a sneak peek. That's something I have just finished this week. It's all about exposing the Globies. I'm sure you guys will love it. So yeah, tune in for that.
Yeah, the lineup for this week is Monday at 8 p.m. Eastern, Celestial Theodolite episode number 38. We're going to be breaking down some central angle theorem and going over the recent revelation that I had 4 days ago. You can learn, if you want to learn more about that, you can see the in-depth breakdown I had over here on this video, but returning back to the live here. And then we have our Tuesday Ether Roundtable 114, which is going to be our yearly recap. And then after that, Man of Stone is going to be doing a video premiere for his release that he was just talking about, exposing the globularist. And then we're going to do the trivia hosted by Man of Stone at, I think, 11 p.m.
Shortly thereafter. I don't know what it's actually going to be. Just call it a healthy Tuesday night triple header and just be there, gang. It'll all just flow end to end, I'm sure.
Yeah, by 10 p.m. Eastern, we should be rolling in on the trivia because the recap's not going to be like it was today. Sorry about that.
Fair enough.
I'm just so proud of everyone. All right. We'll see you guys on the return and throughout the week.
And have a happy new year, guys.